Okay, let's review what we've done before. Back to what?
Basics. Ohm's law.
Ohm's law, there you go. Just read the
Slides.
okay, we talked about our battery cable and how they were really some really poor things that can be done. But this is a fuse that you can put in your line that goes to your rig. Going from, if you're doing a mobile rig in your vehicle, you should run a 10-2 wire with a case that covers both wires on the outside. And it should be number 10 wire. And you can get this in either number 10 or number 12 wire. And you should have as short a lead as possible going up the terminal. There's only one, you just want to make sure that the positive terminal cannot get shorted on anything. But there is one caveat that I haven't mentioned before. If you get it too close, you can have the battery acid actually damage the fuse holder.
Hey, and you didn't mention this before, but I've seen where some people have a fuse on the negative side as well. Is that recommended or necessary?
Oh,
Yes.
absolutely, it's necessary. I'm sorry, I did not mention that. And there's a reason. Your number 2 or number 4 battery cable going from the battery, the negative side down to your block. If that ever falls loose, it'll take whatever route that it can to start the engine. And if you got a number 10 wire with 150 amps through it, it'll burn it out. And your radio is grounded to the chassis of your rig. And that negative wire, if it doesn't have a fuse in it, will ignite. And that has happened. And I have had the, in fact, I was going to bring it, I forgot, I've got the terminal that I cut off of my negative lead to on my Suburban, because it was bad, and I couldn't start the truck and ended up having to replace the terminal. So I hope everybody's pinned on me. And you're not?
No, I'm very focused.
Oh, okay. Well, you don't, those of you here don't have computers. Or shouldn't. Today, we're going to talk about algebra basics. How many people brought the paper that I sent out? Is there absolutely nobody in this room that brought a copy of that paper? If you have some algebraic disease, which is easily developed when you're in high school because of the way they teach it, I can understand. And I see Bruce grinning back at me back there. I got thrown some things. I remember when I was in college, I got thrown some things that just, I was good at math, but I did not understand differential calculus. When I found out from somebody else that the teacher who was going up there doing all these proofs wasn't even doing it correctly. And then I had to try to change classes, get somebody decent to teach. But anyway, we have our various difficulties with problems. Now, I designed this to show you how simple algebra is. If you don't get it, don't worry about it. Go online and download those things I've been trying to get you to download and memorize them. The circle with the triangle of the 3 things, the voltage on the top and I and R on the bottom, or E on the top and I and R on the bottom. That's the one that you have to memorize. And you can use that by putting your thumb over it or whatever method you do to come up with the right formula to figure out something. So you got a choice. figure out how to figure it out algebraically, or figure out how to just memorize it and know the right one and how to apply it. So if you don't get this tonight, don't worry about it. But you do need to memorize it. The other. But this is, here, now look at this. Can everybody agree that A equals A? Equal means they're equivalent. N equals N. How about scissors equals scissors? Anybody got any problem with that? Well, let's multiply both sides by 3. So you get 3A equals 3A. Now let's add scissors to both sides. You get 3A plus scissors equals 3A plus scissors. It's still equal. If you do the same thing to both sides, it stays equal. So let's divide both sides by N. So you got 3 alpha plus scissors divided by N equals 3 alpha plus scissors divided by N. They're still equal. So if you just do the same thing to both sides, and it doesn't matter if it's scissors, elephants, or monkeys. As long as you do the same thing to both sides, it's the same. And a lot of people, they get all hung up on what they're supposed to be doing, when in reality, this is the simplicity there is to algebra. So let's take a look at the next slide. Now let's undo it. So how do we get rid of the N? Since we're divided by N, if we multiply both sides with an N, the N's will cancel out. So you multiply the left side by N and the right side by N. And then you end up with 3 alpha plus scissors. So we got, somebody's got their radio on in the background. Anyway, so if you subtract scissors from both sides, the scissors go away and you end up with 3 alpha equals 3 alpha. Now, my big question is, how do you get rid of the 3's? Somebody.
Divide by 3 on the
Divide by
side.
3 on both sides.
I mean, that's all there is to it. So let's now turn to the next page. Now, if you people out there in Zoom land have not got this, you got the email with it. Now, hopefully, here, actually, I'm going to turn this around a little bit. Here's our first problem. Let's figure out what's going on. We know that E is equal to IR. So E or the voltage is equal to the current times the resistance. So if the resistance goes up, the voltage goes up, or vice versa. If the voltage goes up, the current goes up. Okay, but we know what E and R, and we want to know what I is. How do we get it by itself? Solve for I. So how would you get rid of, I is over there with the R. How would you get rid of the R?
Divide by R.
Divide by R. How many people would agree with that?
Yes.
Yes. Okay, so divide both sides by R. So you get E divided by R equals I. And I want, I have written down here, show each step. In fact, I should be showing that. So we've got E, and I got a pen that doesn't work, equals IR. So if we divide, I'm going to get this down here a little closer. If we divide both sides by R, we put an R here and an R here. This R divided, what is anything divided by itself?
1.
One.
So these cancel. This is I, of course, times 1, which is I. So this here is equal to E, and excuse me, I'm really shaky tonight. Divided by R is equal to I. Now, it says now solve for R. Let's write it again. We get E equals I R. Which one do we want to get rid of?
The I,
The I. So what do we do?
divide by I. Divide by I.
Divide both sides. Excuse me, this wasn't supposed to go all the way across. And I here. So the I's cancel. So we end up with E over I equals R. And if you've got that little circle thing, this thing right here with the line across, and we got E up here, and we got I and R. And that's something easy to remember. Remember E equals B. Electromotive force is measured in volts. So let's try this again. And honestly, the only way I remember Ohm's law is this: I equals E over R. And if you ask me what it was for I couldn't tell you without sitting down and doing it with algebra.
Could I remind everybody to mute your mics if you could, because your image comes up if you make any noise. Thank you.
Everybody should be pinned on me. And look, I see what happened. Okay. Thanks, John. Okay, now we know what I and R is. So we know what this is and we know what this is. So we want to find out what E is. So how do we get rid of the E? Or I mean, yeah, get the E by itself, excuse me.
Multiply both sides by R.
Did everybody hear that? Somebody else, you are correct. Did somebody? The R cancel. So we end up with R times I is equal to B. Anybody got any questions on this? Okay. Moving on, an application. We have a resistor that's 10 ohms. We're going to connect it across the car battery. How much current will flow through the resistor? Somebody tell me. How we should proceed.
Mr. Cotton.
Go ahead, Chuck.
Well, you've got E equals IR, or that's what I started with. So you know that the car battery is 12 volts. So the E becomes 12. Your I, it's 10I, I times 10, 10I. So then
No, it's 10 ohms.
yeah, 10 ohms times
I times I.
Yes. I just left the units off. I'm sorry. Yeah,
Yeah.
bad.
But shouldn't we create the proper formula first?
Well, I started with E equals IR.
Yeah, but that doesn't tell us what I is.
Oh,
We want to know what I is.
I is 10.
No, R is 10.
No, I is 1.2.
Right.
He wants to know.
E over R.
Oh, he wants to point. Sorry.
Yeah, now here, allow me. Chuck, you're figuring that in your head and you're doing it correctly. I mean, you've just done it enough that you know. The problem is when you're working with algebra, you should put down every single step until you get really good at it. Because what will happen is if, yeah, you did in your head.
No, it's on paper.
I can't see your paper. Anyway, you need to put every single step down until it gets so familiar with you, you can do it in your head. So if it's I equals E. Oh, shoot. Let me try again. No, E
Equals IR.
equals IR. Okay, so what we want is I. So how do we get I by itself?
To get rid of the R.
Divide by R.
Divide by R.
Divide by R. So we divide both sides by R. So the R's cancel out. So you get E over R is equal to I. So we know what E is. E, how much is E?
12.
12.
12.
No.
Actually, it's probably,
12.
it's 12.6 or 13.8 or 14.2, depending on whether your car's running or not. But we'll call it 12. And R is what?
10.
10. So now that we've got the formula, we substitute. So we can go, we know what E is. That's 12 divided by R, which we know is 10. And that's equal to what I is, which is equal to 1.2. Sorry about I'm really shaky today. Anyway. Any questions about that from anyone? Oh, yeah, there we go. Solve the formula for what we do not know. Now substitute the values for the letters. This is called substitution, and then solve. That's the steps that you take to do algebra. Okay, we're going to look at power. Power is equal to IE or EI, either one. We know that our heater is 1500 watts. So how much current does it draw from the wall outlet? Now, what do we know?
Power.
We know the power.
In volts.
So what we want to know is, what do we want to know? I. So we need to solve this for I. So we take power is equal to IE. And we want to get I by itself. So what do?
Divide by E.
Divide both sides by E. Put E here is equal to IE over E. The E's cross out. So we get power over E is equal to I. Now, how much is P? Well, how much power do we have?
120.
The 1500 watts was correct. That's the power. What is E, the voltage?
70.
Somebody said
120.
120, correct. That's, by the way, that's AC RMS, root mean squared. We're going to get into that later. So that's equal to I, or you could write it this way, I equals 1500 over 120. But who's got a calculator?
Okay. I was doing the next one.
Let's see here. 1500 divided by 120 equals 12.5 amps. Has everybody had enough time to cogitate on that? Okay. Now there's another thing in algebra that really helps you figure out what's going on. That's called substitution. So we know that power is equal to IE, the voltage times the current. We know that our transmitter is putting out 70 volts peak. We also know that our load is 50 ohms. How do we get our answer? Okay, what we don't know what I is. Let's find something that gets rid of the I. So I is equal to E over R. We know that, right?
Mhm.
So we can replace I with ER. So let's do that. We got power is equal to I. I'm off the screen, sorry. Power is equal to IE. I is equal to E over R. So we can replace the I here with this because they're the same. So we end up with power equals E over R times E. So that, do we have anybody smart out there to tell me what that is? Power equals E squared over R. E squared. Squared, that means E times E over R. So that's how we substitute to end up with what we want. Now, this one's going to be a little harder for you to get. And we are going to illustrate this in class, not tonight, because we don't have the time to do it. But power is equal to E squared over R. But let's say that we have a transmitter that's transmitting into a 50 ohm dummy load. And we've got an oscilloscope looking at it. And here's the scope. And here's the signal on the oscilloscope. Please forgive my shakiness. This right here is 0 volts. This is plus 100 volts. Now this is AC, so it goes up and it's a peak of 100 volts. And then it's a negative here of minus 100 volts. That's called peak to peak. Now, ladies and gentlemen, I am showing you something that can be extremely useful to you. Please pay attention. So how do we figure out what the power is of the output of the transmitter? Does somebody want to tell me? No takers? Okay. E, you take E and you square it. But you don't take peak to peak, you take the peak. But there is a caveat. And I got to tell you a story. For about 6 months, I was checking transmitters, and they're all coming up with 200 watts. So here we got a peak of 100 volts. So let's put in 100 times 100 divided by 50. And we'll get out my calculator here. We'll clear. And we'll do 100 times 100 divided by 50 equals 200 watts. But that's not the right answer. I hate to tell you, my last class, one of my students straightened me out. The FCC has arbitrarily, and it's probably a good arbitration, that it's the RMS value of the peak. So to get the RMS value, you take and you multiply 100 times 0.707. That will give you the RMS value. Now, the root mean square is what the, if you're looking at this, if you had DC running through here like this, the power of this would be the same as the power of that. And that's what root mean square is. Don't worry about that right now if you don't get it, but we will discuss this in detail later. Okay? So you take 100 times 0.707. So I'm going to take 100 times 0.707.
70.7.
Correct. Now I'm going to turn this over, see what my machine did. It went to something. So I've got a thing here that says x squared. So I'm going to hit x squared. And that comes out 4,998.49. In other words, 5,000 times, no, excuse me, divided by 50. And that equals 100 watts. Almost all of our quote barefoot transceivers that are HF put out 100 watts peak envelope power. And that's how the FCC defines it, and that's how we do it. And we are completely set up in this room to do that work. So if you ever have any question about how much your transmitter's putting out, you can come over here, set it up, use our dummy load, use our oscilloscope, and figure out what the power is doing. And I would love to have a whole bunch of you learn how to do that, so I don't have to. I don't, honestly, I don't mind doing it.
Well, that one calculation is a key calculation.
That's absolutely true. So actually, E is equal to the peak voltage times 0.70. Wait, I'm sorry, 70. Oh shoot.
0.707.
707. There. So you take E, the peak voltage times 0.707, and you square that, and you divide it by R, which most of the time is 50 ohms, there should be, and that is your power. Okay, one more.
So what I don't get is why are they using root mean square? I mean, they just arbitrarily picked root mean square.
Well, that's actually closer to what the real power is.
Oh, so in order to get to the real power, they had to figure out what the factor was. Root
Correct.
mean square.
Yeah, our RMS is a very common value, and we'll learn a lot more about it later in the course. And let's skip the last question on there because we're running low on time. How many of you remember this? I And I kind of hear,
We did that last time.
Yeah.
yeah, well, this is about the fourth week of doing this.
Yep.
The schematic that is on the left side, the battery and the three resistors are in
Series.
series. Good. And the resistors that are on the right hand are in
Parallel.
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 Good. Now, the thing about Kirchhoff's law, and you don't, as I said, you don't have to remember Kirchhoff. But he's the one who came up with this stuff. The current through R3, the current through R2, and the current through R1 are all the same. And the current through the battery is the same. So in this loop, there is just one current. So the voltage across R1 is the current times R1. The voltage across R2 is the current times R2, right?
Mhm.
It's the same current every time. The current through R3 is, the voltage across R3 is the current through R3 times R3. So that's three different voltages. If you add those three voltages up, if you add the voltage from here to here to here, and then you subtract this voltage, it should come out zero. And as I said last time, if it doesn't come out zero, call in several scientists because you have created a miracle. God, most of the times, has everything work normally into his laws. Every time, every once in a while, a miracle occurs. So I want one of you to share a miracle with me. Now, on this side here, it's something else going on. The voltage across every resistor is the same. It's this voltage across here. With our little regulator, when we put stuff in parallel, it's got 5 volts across every single one of them. So the current, we know, if we know what R1 is and what the voltage is, we can tell you what the current is through R1. And we can do the same for R2 and the same for R3. I1 plus I2 plus I3 equals the current that's going through the voltage source. Or it's the current that is right here where it says I. They all add back together. And now this is one thing that I have not said to you, but if you have a combination of this, if you had, for instance, over here on this, you had a resistor that went from here to here. So you have these two parallel resistors. What you do is you calculate what those two resistors are and then treat it as if it's like this. So you can combine it down to all in series or all in parallel. So that's the last we're going to get of that for quite a while. If anybody has any questions, call me at home. Not before probably 10 a.m. Yes, Bruce, you know. Anyway, and talk to me and I'll help you work your way through it. Now here I've changed this just a little bit, but here are the schematic forms of voltage sources. Here are batteries, and these are voltage sources, and this voltage could be anything, plus or minus a microvolt or plus or minus 1,000,000 volts, or it could be AC, alternating current, whatever that is. Here's an alternating current source. Here's a big dam that generates, how much are the power lines? Like 120,000 volts? Does anybody know? I don't know. When coming from this here, they run extremely high voltage and a small current. When you get to a transformer, it transformers it down to a low voltage and a high current. But that's something else we're going to learn later. So it comes out our walls 120 volts AC. So then we provide a power supply that hooks up to our radios. Then there are other power, that's a power source. We've also got, here's a schematic of a battery like this and a load. Here are a couple AA batteries. Here's a automotive 12-volt battery. By the way, for all of you that are in MCOM, if we get wiped out and there's a pile of cars there, lift those hood and pull those batteries. Because that was going to provide you with a lot of power. And remember that. I mean, those cars are not going to do anybody any good. If you're feeling really guilty about it, leave a note there. I owe you a battery. But under those circumstances, I don't think anybody's going to complain. And then this is my favorite one, the three potatoes hooked up. You put different kinds of metal in here and then hook them up in series. They even light up this little light bulb. So anyway, that'll be the last of that. And this is going to be the last of this one too. But I just keep repeating this, so hopefully you guys can get the picture of what these things do. Voltage, which is electromotive force. He's trying to force current through the conductor. You see the conductor here and here. And then you've got ohms, which is the resistance in the wire or a resistor that's in the wire. And it's squeezing this off, trying to keep the current from going through. And then amp is the current that it's going through. So that's kind of a picture of what happens in Ohm's law. I, which is amps, equals E over R. The higher the R, the slower the amps. The lower the R, the higher the amps.
But I don't understand is when is E used versus when is B used? Why do we have these two terms that mean the same thing in the formula?
When I was young, I equaled E over R.
Yeah. Not
Period.
anymore.
That's electromotive force,
Yeah.
which is measured in volts. Somewhere along the lines, people started using V because people couldn't remember what a E electromotive force was. They're identical. They can be used interchangeably.
But I mean,
One
is
is what it
there some
No,
oh,
no. No, it's strictly up to the person who's using it. And if you go online and you look up Ohm's law, you can see all these things. Some of them are using E, some of them are using V, as in Victor.
right.
It's a matter of your schooling. I guess you could say I'm just an old-fashioned guy. Next.
Well, back when we were in school, Joe, if we said V equals IR, you'd get your hand slapped by your teacher.
That's true. And probably with a ruler.
Yeah.
Or a yardstick smack. No, they wouldn't put up with that. Okay, power. Oh, first. Here is the definition of resistance, and I want this to sink in. We have looked at resistors, all kinds of them. Well, that's just one form of resistance, but opposition to current by conversion into other forms of energy. With resistors, they turn the current into energy. So if it's high resistance and it's high voltage, it's going to put out a lot of energy. Such as heat, and it's measured in ohms. Any questions at this point?
Yeah, sorry, just to come back. So the heat that is created is measured in ohms? Is that, did I
No,
understand you to say that?
that would be heat in watts, actually.
Yeah,
Yeah, because power is IE or IV,
mhm,
as in Victor, voltage.
mhm.
So it's the voltage times the current is equal to power. But before we go on, resistors come in different values. And it used to be when you worked on old radios, most of them were 20% resistors. If we're talking about 100 ohms, that meant 80 to 120 ohms. 5% is 95 to 105 ohms. It's within that, the resistor is good. And 1% resistors, most of the resistors I send out to everybody are 1%. It's amazing. I was online and I looked, and for about $6, you can get literally several hundred resistors for $5. You know, it's anywhere you go probably from about $4 to $12 or $15. You can get whole sets of resistors. So they're very inexpensive. And then there's the value. If there's in a anything 5% or less is just a three band resistor. And by the way, you can go online and you can go resistor color codes, and they'll come up with dozens of examples of a color code chart. So if you've got red, yellow, brown, that's 2, 4, 0, 0. 2400 ohms. That's how it works. So, and then the fourth band is the value. If there's no fourth band, it's 20%. If the fourth band is silver, it's 10%. If the fourth band is gold, it's 5%. But when you get down to the 1%, you have to have 3 active digits. Did you not understand that, John?
I did.
So I don't understand, what's an active digit?
Here are resistors, and here are the color codes. So here we've got 1, 2, 3 bands. If it's a 20, well, this one is showing, oh boy. You guys can't see this, but on my screen, I got something stuck in my way here. Green, as you can see here, is a 5. Blue is 6. Brown is 1. So that is the multiplier for a 5 or lower value resistor. So we got 5, 6 multiplied by 1, 0. So that's 560 ohms. And it's gold, so that means it's a 5% resistor. Now, if you go to, I don't know what's going on with this bottom one. But if we go to the next one, if we were in a 1%, that would be 5, 6, and then orange is 3, 5, 6, 3, 0. So that's 5,630 ohms at 5%. But we ought to actually have, see down here, it says 1% is brown. Most of our resistors are 1%. So this one right here would be brown, which would give you 1%. Did that answer your question?
Well, I still don't know what an active digit is.
Oh, these two here are active digits.
Oh, I see, okay.
This on this one here, this one, and this one are an active digit, and that's a multiplier.
And how do you know that? Oh, that little form tells you.
Well, I'll be right with you, Chuck.
Yeah.
Hey, I've been doing this since I was 5 years old.
Okay.
And I can't tell you why I know that. Chuck,
Well, I was going to bring up that this diagram is all well and good, but for a lot of people who are not familiar with them, they'll say, well, which side do I start with? Which is a little bit what Ann's referring to here, you know, as to that. So the only way I can put it so that you know which ones you're going is that some, they will have them down at one end. And the other ones, you can look at the end ones, and if it's brown, silver, gold, then you know that that's the end of it. That's the help me with
oh,
it.
correct. Yes, that's the
tolerance level.
The tolerance. So you start at the other end to go down to figure out what the bands mean.
correct. You can see with this one that everything favors, well, I guess it, yeah, that, no, I guess
No.
it doesn't. Well, there's a blank spot here. I guess, meaning this is farther away than these. Anybody got any other questions about resistors? Next slide. Electrical quantities. Now here, there's one thing that I want you to remember. We've got ohms, volts, ohms, and amps, and you've heard me refer to kilo ohms, mega ohms, milliamps, microamps, microvolts. Remember this, and this is something that you just flat need. If you don't know it, you need to memorize it. Here, I'm going to get this out of the way. Micro is 1/1,000,000. 1/1,000,000. So that's micro. Milli, which is an M. In fact, let's go back to micro. Micro is, see this U right here? Actually, the symbol has this U. Has this U with a little tag coming down here. But because you can't find that on a normal keyboard, that's micro. And you go to milli, and it's a small m. That means 1/1000th. Then you have normal volts, ohms, and amps. And then you have kilo, which is 1,000, and that's K. So if somebody says you got a 47K resistor, that means it's 47,000 ohms. And that's a very common thing to hear. People just call it K. So 47K or 2.7K means 1,000 ohms. And then there's megohms. That's 1,000,000, and that's a large M. Notice we got a large M here for million and a small m here for milli.
So I noticed on the ohm line, it didn't go down to micro ohms. Is that because there are no micro ohms?
In a cryogenic lab, you can get down to micro ohms. But you know, the wire that I showed you for hooking up that had the fuses in the wrong place, the resistance in that wire is in milliohms. There is resistance there, but you don't, I have never seen anything in real life that's micro ohms. But you got milliohms, ohms, kiloohms, like 2.7K, and megohms, up to about, well, 3 megohms is a lot for a resistor. Some of them do go higher than that, but that's really rare. So we're just about out of time for this. We are going to, when we come back from break, we're going to cover watts again, and we will have an illustration of your BU meter on, or your S meter, excuse me, on your radio. And then Daron, after that, we're hopefully we're going to get into capacitance, and Daron's going to be able to demonstrate series and parallel capacitors.
I hope you're right.
Anyway, everybody take a break. Power in watts. Let's just review. Power is everything. The heat generated by a resistor, power output from your power supply, amount radiated from your antenna, how much power does your handy talkie put out. Those are all things in there. It's all measured in watts. So power is equal to IE. What is E?
Energy.
Electromotive force.
Right, and you can substitute that
Voltage.
with V, voltage. Just remember, if it's E, it's either excuse me, E or V. So there is this. Now, if you didn't get the message, thank you, John, for finding it. I sent out something that had Ohm's law. It had a picture similar to this. And what else did it have? Oh, it had Ohm's law, and it had the circle with the E over I and R, and it did all that stuff in a little schematic. The which one was it, John? It had the square root of I
Times R, I think. It
times R was supposed to be, I think, the power, wasn't it? I don't know. One
Yeah,
of
I'm
them was
looking it up now.
wrong. This one, if you find this one online, this one's correct. So we have a choice of figuring it out through algebra or memorizing something like this,
It was under volts, and it was a square root of I times R, and which is wrong.
which is wrong, definitely wrong. And I was
So-
really shocked.
It should be P, the square root of P times R.
What is it supposed to be, John?
I think it was supposed to be the square root of the square root of P times R with everything under square root. I think that's what it was supposed to be.
Yeah. It was PR, John,
Yeah, square root of PR.
the square root of P and R times each other. So, but we're not now. This is when, if you got resistance, and they're in series, you just add them up. And by odd, I mean not the same value. It could be the same value. It could be 100 plus 100 plus 100, which is equal to 300. Or it could be 100 plus 50 plus 20, which is 170. But that's the correct way to add them when they are in series. When they're in parallel, if there's two, if they're the same, if it's like two 100 ohm resistors in series, I mean in parallel, excuse me, I'll get this straight someday. You just divide 100 by 2. If there's 3 in parallel, you divide it by 3. If there's 4 in parallel, all 100 ohm resistors, you divide by 4. That's easy. But if they're a different value, you use this formula. Now, when you're taking the test, sometimes if you can't remember what the actual formula is, you're given 4 choices. 2 of them are obnoxiously wrong. I mean, it should be real obvious. But if you got 2 resistors in parallel, the value is always less than the lowest value. If you had 100, 50, and 20 ohms in parallel, the resistance is going to be less than 20 ohms. So if you've got an answer that's, I don't know what that actually is. I mean, we could calculate, I don't want to do that. It's going to be less than 20 ohms. And the same applies here. Now here you've got multiple resistors. So if you had R1 was 100, R2 was 50, R3 was 20, the resistance is going, and forget R10, the resistance is going to be less than 20 ohms. If the smallest resistor is 5 ohms, the resistance is going to be less than 5 ohms. So that's just one way to, you know, if you can't get it that way, you can figure it out another way. Thank you, Scott. Scott's back there shaking his, now, on to DB. Oh.
So why is that? So the resistance is creating heat, right? Does it have to do with the amount of heat that's being created? Why is it always going to be less than the smallest? I mean, I know the formula will work out that way, but just I'm trying to understand what causes that.
If you have a 20 ohm resistor and you put a 50 ohm in parallel with it,
yeah,
the resistance is going to be lower. So the lowest resistance is going to be lower than that. I don't know if, but go ahead, Chuck. I'm Scott.
Yeah, the only thing I can say is that, you know, work 3 sets of R numbers using that equation, and it'll always come out less than the smallest one. And that's just from your experience that you know that, and that's a good hint. I didn't realize that myself, and
Yeah, it just, I've known that in the past, but I had forgotten it. By doing this, I recognize that. But and actually, what you're saying, this is from a parallel resistor calculator. This is actually, if you go online and you enter in your search engine parallel resistor calculator, it'll come up with several sites that you can go to, enter any one of the number of resistors that you've got, and it'll tell you what the parallel resistor, what the parallel resistance of all of them are. It's a lot easier than figuring out R over R, 1 over R1 plus 1 over R2 plus et cetera, and then all of that under 1 and divided. I mean, that's a lot of work to do. I mean, you can do it every time if you can remember this formula. And when you take the test, if they have one of these, you can sit down with a calculator, not your telephone. The telephone can have too many answers on it, but if you have strictly a calculator, even if it's scientific, you have to erase the memory. But other than that, you can use a calculator to figure out what it is. Well, let's move on. Decibels. Most, or I shouldn't say most, but many people have no clue what dB means, what decibels are. And in amateur radio, you're talking about it all the time. So this is something that I wanted to show you. Let's look at this formula right here. Let's clear this. Now the formula was 10 times the logarithm of a power ratio. So let's talk about a QRP person. They typically go from 100 watts down to 5 watts. So that's a power ratio. So it's 100 divided by 5 equals 20. So it's a ratio of 20 to 1. So now this is a very magical thing. Come on, magic work. It's making me sweat. So we've got an answer here of 20. And here, right here, it says, oh, that is not what I wanted.
Clear.
Yeah, that's not what I wanted either. Let's get our 20 back up here. It says log 10, log base 10. So we hit log, and that comes up with 13. So it's 10 times the log of the ratio. So 10 times that. So we multiply by 10, which is real easy to do, and that comes out 13 dB. Now I'm going to show you something in a little while that will show you the difference that 13 dB comes when it comes to your radio signal coming into a receiver at the other end at somebody you're talking to. Now there's another one also, and let's clear. Now I'm going to go back, excuse me. Oh, wait a minute, back over here. So if we take voltage, and we do the same thing, we take 100 divided by 5 equals, and we get 20. So we go over here, and we take the log of that, and we multiply that by 20. So we end up with 26 dB. But that would be if you're dealing with voltage, not power. Voltage and power are two very different things. Or if you're talking about audio levels. So what we're going to, in a little bit, we're going to look at a radio with 50 microvolts going into it. Now, but first, before we do that, I want to talk to you about how important dB is to amateur radio. I mean, everywhere you turn, something's going to be talking about dBs. Whether you're talking about antenna specs, the loss in the cable, the gain in amplifiers, the path loss to the moon and back, which, by the way, they're in the middle. It's at 250 dB. That's a major loss. That's why it gets fairly spendy to get involved in doing EME work, Earth, Moon, Earth. And audio microphones. They talk about the dB of, you got a pattern. Here's our antenna patterns. Here's the horizontal pattern, and you can see got a Yagi. It transmits in one direction, and off the back, it's almost nothing. So if you're looking at your power, you'd be going across here like this, and that's major, where you're radiating, and you're hardly getting anything but from the back. But very often there are lobes like this here. We will get into great detail on this later. You might have some signal coming out from over here. But anyway, here is the attenuation in coax here per 100 feet at different frequencies. Over here is an advertisement for an antenna. Here's a vertical 2 meter, 70 centimeter, and it's gain in its dB from a dipole, which is 2.14 gain, or a gain from, it's I. What is I? I forgot. Somebody?
Current.
Isotropic.
Isotropic, thank you. From an isotropic antenna, which is a theoretical pin-sized antenna, the head of a pin. But there is no such thing in the real world. Anyway, Now, let's talk about dB. When you're talking about power, now, you can use your calculator like I did. You can use that formula and your calculator to calculate it out, but you don't really need to do that. If you're talking about power, let's say you start out with 5 watts and you double that power, then it goes to 10 watts. Well, that's 3 dB of gain. When you double it, it's 3 dB. So if you go from 10 to 20, that's 3 more dB, or that's 6 dB gain. So if you go from 20 to 40, that's 9 dB gain. But you've gone from 5 to 40, that's 9 dB. If you multiply it by 10, which would make it 50 watts, that's 10 dB. And when you do it on your calculator, it comes out exactly 10 dB. When you're doing these 3 dB, 6 dB, and 9 dB using this method, it's off by less than 1%. So everybody uses these to figure out what the power difference is.
So double twice, does that mean 4 times or something?
Yeah.
Oh,
If you double it once, that's 2 times. If you double it twice, that's 2 times 2 or 5 times 2 times 2 twice. If you do it 3 times, that's 5 times 2 times 2 times 2. So you get 5 times 2 is 10.
is there some reason we say it this way rather than just times 4 times 6 times whatever it is, or 8 times?
Because you're multiplying it by 2. You're doubling it each time.
Oh, I
It's a
see.
power, it's
Oh, I see.
we're working in powers of 2.
Yeah, okay.
And that's what, when you're working it with the ratio of dB, that's what you're doing.
Right.
Okay, now you can also talk about voltage ratios. But there, for each time you double it, if you go from, say, 50 microvolts to 100 microvolts, that's a 6 dB gain. But actually, let's turn it around. If you go from 50 microvolts down to 25 microvolts, which is half, that's 6 dB. And if you're talking about voltage or you're talking about volume, believe it or not, people can just barely hear 6 dB change. If you double it twice, so in other words, you go from 25 microvolts down to 12.5 microvolts, that's 12 dB. And I'm not going to try to figure that out. 6.25 would be 3 times. You divide it by 2 each time. That's 18 dB. And of course, if you do it by 10, that's 20 dB. And for those who work with oscilloscopes and might run into Tektronix attenuators, if it says 20 dB, that's 20 dB voltage, not power. So if you're working with an oscilloscope, expect it to change it by 20 dB, which is 10 times. So now let's see what the next
So
slide
the
is.
ratio, what is the ratio? It says a ratio of power, but what are the 2 power?
The ratio of power would be like from 5 watts to 100 watts.
Oh, whatever it is. Okay.
Whatever the ratio is.
Okay.
And by the way, I mean, dB can be, it can be dBm.
So it's really a change, right?
It's a change. dB is a change. It's a ratio of one power to the next. And if you do it, like if you went from 100 watts down to 5 watts, if you calculate it with your calculator, it'll say negative 13 dB.
So we would do this if we wanted to use less power and figure out what the
dB change.
quality would be, the
Yeah,
quality of the
uh,
voice would be.
Most of the time, we don't use that in normal operation. But if you're trying to work the repeater and you got good connection, nobody's ever going to worry about dB. But if you're just barely getting every time, then you want to gain something. If you get a Yagi antenna, that's an antenna with several cross pieces on it, maybe only even 3, and you aim it at the tower, vertically polarized, you have a much better chance of getting in. And an antenna like that might be 6 dB gain or 9 dB gain. Yes, Scott.
Yeah, another big thing that you use dB for is when you're talking with someone on the air, and they want to know what their signal strength is reading.
Yeah, that's your S number.
Yeah, that's your S number, your signal strength. And so let's say you gave him a 5 and 9. Okay, if he only had a 5 and 7, you know, what's the difference between a 5 and 7 signal and a 5 and 9?
See the meter right here? Here's the S meter on a 10-tech radio. Here is S9. Now, Scott, say your thing again.
Oh, I was just saying, you give maybe you give a guy a 5 and 9 a signal report, which means his signal strength is 9, you know.
S9.
S9, and if you actually only got let's say you had 7, or excuse me, I gave him let's say I gave him a signal strength of 7.
Yes.
Okay, and if you wanted to improve that signal so that when we talked, he would actually get a signal report, a much stronger signal at 9, S9.
Yes.
You know, well, what's the change in power that you would have to get a 2 dB difference?
No, that's
Or
2 S units.
2 S units difference.
That's actually 12 S units, or 12 dB. V. That's voltage. 12 dB. And let me demonstrate. Now listen. I am going to reduce the output of this signal generator to drop it down to 8. Okay. Can you guys hear any difference in the audio level?
A little bit.
Not really.
Not so much.
Somebody's got sharp ears.
Yeah.
It's just barely different. That is 6 dB. So if I reduce it further, and I reduce it down to 7, can you hear the difference?
Yes.
I mean, I can't. I
Yeah,
can't
not
tell.
very much.
I can't tell the difference. I mean, it barely changes.
Yeah.
Now, look, we're going to go from 100 watts, which is up here at S9. Okay, and then we're going to go down to 5 watts, which is about right there. Just barely below 7.
It's not a lot of change.
Yeah, most of the time, if you've got good path between the people and low noise, you can run barefoot and people can hear you.
Yeah.
Now, I'm not a barefoot guy. I mean, I'm QR. I mean, if they got this wrong here, I'm gonna go 20 over and throw in 1,500 watts, you know. Of course, I don't do that, but I mean, that's what I feel like doing, you know. But for
so
QR,
this is important because we're always supposed to use the least power necessary, right?
good, correct. And I say my QRP, which is higher power. I mean, excuse me, QRO, which is higher power. So anyway, do people get the picture here? One thing, when you're talking about dB, it's very important that you understand what we're talking about. When we're talking about S units, we're talking about each S unit is 6 dB. Let's go down to 1 point.
But
What?
Joe, do you really need to know the value or just that you're moving in the right direction?
Actually, honestly, you only need to know that you're in the right direction. But if you're trying to correct some situation with what's going on, you need to understand what's going on. And you need to understand what people are talking about. It's a matter of when you hear it, you know what they're talking about rather than going, what's dB? I don't know what dB is. People keep talking about it. Chuck.
I think that people should realize that Joe's giving you a good information on dBs here. And the amazing thing is that the ARRL extra handbook covers dB on one page, and it's only referring to antennas, Yagi antennas. And so what Joe has been telling us is what's going to really be helpful. And if you need more information, you're probably going to have to go to the handbook and look some things up for dB on that. Just saying the handbook for the extra class it deals with it on one page.
Yeah, I'm trying to put together what you'll find throughout the handbook. I mean, dB is a concept that you should get your mind around and understand what it means. So remember, there's dB power, which is what we use most of the time. If we're looking at S units, we can talk about S units, but understand that one S unit going from S9 down to S8 is practically no difference at all. But that's 6 dB in voltage.
I always thought of it as a measure of loudness.
That is in volume, which is one of the ones that is for 20 log the ratio. That is what it is.
So how does that relate to the power that we've been talking about? So the more power, because it's not necessarily the more power, the louder it gets, or.
Well, yes, but they're two different measurements. And so they're measured differently. Power is the current times the voltage,
right,
which gives you the power. The dB for voltage or audio is strictly the voltage or the apparent sound level.
Oh, I see. So the loudness is on the voltage side. And
correct.
Okay.
Yeah, are you familiar with a VU meter?
No.
A VU meter is what when they have a radio station, they have meters that they go back and forth like this, and they're VU, and they got 0 dB, and you're not supposed to go above 0 dB.
Yeah.
That's voltage related, and it's audio level related, and that's 20 times the log of the ratio. So that's where that's used. I don't want to confuse you, but there is dBm. That means 0 dB is a milliwatt.
Mhm.
There's dB, just plain dB, which is a ratio, whatever the ratio is. There's dBV, which is the voltage, and there's dBu, which is what you find in VU meters in professional recording equipment in sound stages and stuff like that. But that's all nitty gritty detail that we don't need to know right now. Now, I think next we've got capacitors. Capacitors. What time is it?
Quarter after.
Okay, we're just, I want Daron to give a quick demonstration, but first let's take a look at capacitors. Here is a capacitor. And this is basically what they are. They're two separate metallic plates with a dielectric in between. Dielectric is an insulator. It can be air, vacuum, paper. There's all kinds of materials that are used to separate the plates, but the plates do not touch. So if you apply DC to this, it will not flow. It's stopped. If you apply AC to it, AC will flow through a capacitor. But we will get into much more detail. I'm going to very quickly go through this. Here's a bunch of capacitors. So you can take a look at these and see the different kinds of capacitors that are available. There's all kinds, and they have all kinds of functions. They can be used for filtering the power supply, the hum that comes from a power supply, it smooths it out. It can be used for an input filter. We talked about that. On like our little 5-volt regulators, they keep noise from interrupting the regulator from functioning properly. All kinds of stuff. Now here's a capacitor. Does everybody remember what a coulomb is? A coulomb is a bunch of electrons, and it's in the number of times 10 to the 16th power, or is it the 15th power? It's a very huge number. So it's the number of electrons at passage of point in 1 second is a coulomb. It's a very large number. But anyway, on the right-hand side here, we've got a lead here on the right-hand side, and this is negative coulombs, or this is the negative side. It's got a bunch of electrons on this plate, and on this side, we've got the positive side with a bunch of holes. So I'm going to come back to this and do this in great detail next time. So now capacitors in series and resistors, excuse me, capacitors in parallel. The way you figure them out is just like you figure out resistors in series. And when you have capacitors in series, you figure them out just like you do resistors in parallel. So, Daron.
Yes.
Take over. Quick.
Wow, Joe.
I know
Well,
you don't have much time, but
I think what I have built here is 3 capacitors, and I apologize for the difference in size. They're what came out of my junk box. It's the way it goes when you scrounge for parts, but they are all 100 microfarad capacitors in series. I tried to quickly sketch it out here. It's the first capacitor, and the second one and the third one, they're all in series. And what do you want to do? You want to check the total figure there, Joe, first?
Yes. Excuse me, I'm here futzing with Zoom, trying to get you into the video.
All right, well, continue futzing. We will try this with the handy dandy meter set on the capacitance setting. We'll start at the negative
So you're
side.
putting them all in series first.
Yeah, they're all in series,
Yeah, now have you tried this?
of course.
Yeah, okay. Well, then it takes several seconds for this meter to respond.
Yeah, it's got to charge up those capacitors to figure it out.
So it takes a few seconds. There it is already. So that's not bad. So you got about 37 microfarad.
Yes,
And each one of those is 100 microfarad, right?
that is correct.
Yeah. Yeah, so now go ahead and hook them in parallel. I had fun getting mine plugged in.
Well, I trimmed the leads so they were the same length. That made it quite a bit easier, but
Yeah, there you go.
so we'll put them in the same vertical column, right?
Correct.
So they're all in the same vertical column, so they're all in series. And then
Parallel.
we can parallel, yeah, that too. And we'll just grab onto the outside one here with the meter.
There we go.
I don't know what the tolerance is on these, Joe, versus the tolerance of the meter. It's a little bit off.
Yeah, it seems to me the tolerance, isn't it something like -10 + 20 or -20 + 50? I mean, it's the
I don't
tolerance
know.
for these is really pretty wild.
I suspect that's the case.
Yeah, what's
But it's-
really funny is the ones that I had, they were right at they were literally within 1%.
So
I
what
see.
are you actually measuring? I mean, that number is what unit?
That's farads,
Oh, okay.
Microfarads,
microfarads.
kind of hard to see up in the corner of the meter there, but
Oh yeah, there's the M, a large M, and an F for farads. Or
that's-
micro.
that's a little U. Yes,
Yeah, that's the little U with the tail hanging down.
right. Microfarads.
Microfarads.
So I'll just take one of those out.
Yeah, there you go. So you get 237. Now these are in parallel.
I'll take one more out.
132 microfarads.
Yeah, that might just be tolerance on these, Joe.
It is. Yeah, the tolerance on that style of electrolytic capacitor is very wide. But
So,
go ahead.
so these capacitors store energy, right? So why is it farads and not volts? Or, I mean, why did we change the unit here?
Shoot.
Were you going to answer that, Daron?
I was going to say it's storing volts, and we can hook them up and charge them and measure the voltage that it stores. But the farads is the measurement of its capacity to do that.
So that the 130 measurement there is microfarads, and that's the size of the capacitor,
Correct.
that particular capacitor. So if he put two of them in parallel, it would be and they're both the same size capacitors, it would be double
Correct.
that reading, and if you 3 of them, it would be 3 times the reading.
Yeah,
of the
Darren?
one.
Yes,
I tell you what, for that big one that's on the bottom.
yes.
pull it out and measure the other two.
Oh, hang on. I was gonna power that up. Let me,
Oh, sorry, I messed you up, huh?
no, it's all right. Let it never be said, Joe, that I wasn't flexible.
Thank God.
See, that's a lot closer to what it ought to be.
Yeah, that larger one.
That one is way out in its tolerance, but it's way over, so for its application, it's no problem.
So should I charge those up?
Not now.
Okay,
We're almost out of time. Ann is asking very good questions. And Ann, can you hang on to that until next week?
Mhm.
Because we're going to get into the details of this. A capacitor is an electrical storage device. It stores an electric field. If you charge it up with a battery or a voltage source, and then take the source away, it will stay at that voltage. Although in time, it'll leak away, but it will keep that voltage on it. So it's a storage device. So it's not, it'll store what you can read with your voltmeter as volts. But if you've got a small capacitor and it's reading 5 volts, and then you put a load on it, you say you put a 1,000 ohm resistor across it, it'll take X amount of time to discharge that capacitor. But if you had a large capacitor, say let's get ridiculous. They have capacitors that they use as a battery, 1 farad capacitors, which is a huge capacitor. They're 5.5 volts at 1 farad. If you put 1,000 ohm resistor across it, it would take a long time for it to empty that capacitor because there's a lot of electrons stored in there. The bigger the capacitor in farads, the more electrons it will hold.
So is the difference between a battery and a capacitor the physical construction? I mean, this is a plate with an insulator, right? But a battery is something very different.
Correct.
Yeah.
Yeah, they're very different. A capacitor, that's a rare application, although it's becoming more common because they've been able to actually create capacitors that big. Most of your capacitors are in microfarads, which is a millionth of a farad.
Mhm.
So if you can imagine having a whole farad, that's a lot of capacity. So folks,
Did
I
Darren
disobeyed,
show you
Joe.
that one capacitor? I think he did.
Sorry, I disobeyed. I charged it up to 5 volts.
Yeah,
and you've turned, what, have you turned it off or you're?
Yeah, here, let me just give it 5 volts again for a second. All right, there, it's charged up. Now it's just leaking off.
Yeah. There's no resistors across it, right?
No, just the meter.
Yeah. Oh, the meter. Yeah, that's 10 million ohms. And it's emptying the capacitor slowly. Folks, we've studied resistance. We are now starting to study capacitance. Soon, we will be studying inductance. Now, those are the 3 major parts, passive parts of electronics. So with resistors, capacitance, and inductors, we can create most everything in the passive realm without amplifiers and oscillators and all that kind of stuff that we do with active devices. So hang in there with us. We're getting this one step at a time. And I'm going to say, well, Lord, I forgot to pray at the very beginning of this. Thank you for all we've been able to learn tonight and having a good time. In Jesus' name, amen.
Amen.
Good night.
Night, Joe.
Thank you, Ann.
Stop the recording.
Thanks, Joe. Thanks, Darren.
You're welcome.